Today, we're jumping straight into Satoshi Nakamoto's 2008 white paper. We're going to dissect the technical problems it found with online commerce at the time, and then walk through the iterative solution it proposed for a purely peer-to-peer electronic cash system. Let's get right into it. So, the paper kicks off with this really clear and ambitious goal. The whole idea is to mimic the way physical cash works, but in a digital world. You know, that ability to just hand money to someone directly with no bank or middleman getting in the way. Now, to really get the solution, we first have to understand the problem it's trying to solve. And back in 2008, the entire system for online payments was built on a pretty shaky foundation: the need for trust. This slide really breaks it down. When you pay with physical cash, that's it. The deal is done, it's non-reversible. But online payments, they have to go through financial institutions, mainly to handle disputes. This means transactions can be reversed, and that simple fact adds costs, makes small payments impractical, and forces merchants to collect way more of your personal info than they should need to. That need for trust actually becomes a huge systemic flaw. So the solution the paper proposes is, frankly, radical. It's about throwing out that fragile trust-based model completely. The idea is to replace it with a system built on pure, cold, hard cryptographic proof. A system where math, not a company, validates every single transaction. All right, so the first building block in this new system is the digital coin. But as we're about to see, this seemingly simple concept immediately creates a brand new and very critical problem. An electronic coin, as defined here, is just a chain of digital signatures. To pass it on, you basically sign a digital fingerprint of the last transaction and add the public key of the person you're sending it to. This creates a public, verifiable history of who owned the coin. So far, this makes perfect sense. And boom, here's the new problem, the gotcha. You, as the receiver, can check the chain of signatures and see that the coin is legit. But how do you know the sender didn't just send that exact same coin to someone else a few seconds before? You can't. This is the classic double spend problem. This is where the real genius of the paper comes in. It lays out this elegant, multi-step process for solving that double spend problem, all without needing a central bank or mint to keep track of everything. So think about it. If you don't have that central trusted authority, that single source of truth, how can you possibly be sure a coin hasn't already been spent? Well, you'd need a way for everyone to see everything, all at once. And that's the first piece of the puzzle. You make all transactions public. You broadcast every single payment out to the entire network. This way, everyone can build a shared, universal history of what happened and when. In this system, the first transaction that gets announced is the one that counts, period. Okay, but a public ledger creates its own headache. If you have nodes all over the world, they're going to hear about transactions in a slightly different order. So, which history is the real one? How does this scattered, decentralized network agree on a single official timeline of events? The answer proposed is a kind of distributed timestamp server. It works by grouping transactions together into what we call blocks. Each block is then cryptographically linked to the previous one, forming a chain. This means every new block that's added makes the ones before it even more secure and harder to change. It's like building a tower, one block at a time. This leads us to the final, really critical question. Who gets to add the next block to this chain? We need a fair way to vote. You can't just use IP addresses, right? One person could spin up thousands of nodes and take over. We need a system that can't be so easily cheated. The solution is proof of work. To add a block, a computer has to solve an incredibly difficult mathematical problem. It takes a ton of electricity and processing time. This makes creating a block expensive, and that cost is what secures the network. It turns voting into one CPU, one vote. The longest chain is considered the true one, simply because it has the most computational work, the most real-world energy poured into it. So we have the theory down. Now let's look at how this whole network actually works day to day. And maybe more importantly, why would anyone even bother contributing their computer's power to this thing? The whole operation runs on this simple 6-step loop. New transactions get broadcast to everyone. Nodes gather them up into a block and start racing to solve that proof of work puzzle. Whoever solves it first gets to broadcast their new block. Other nodes check it to make sure everything's valid, and if it is, they accept it and start working on the next block, always building on the longest chain they see. So why participate? Simple. Incentives. The node that finds the new block gets a reward of brand new coins. They also get to keep any transaction fees that people included with their payments in that block. This creates a powerful incentive based on rational self-interest. It is way more profitable to play by the rules, secure the network, and earn rewards than it is to try and attack the system, which would ultimately just destroy the value of your own coins. Okay, let's look at the math that actually holds all of this together. The paper doesn't just say, this is secure. It actually proves it, mathematically. If an attacker wants to reverse a transaction, they have to secretly build their own longer chain and then release it to trick the network. This puts them in a race against the entire honest network. The paper models this as a classic statistics problem called the gambler's ruin. Imagine a gambler with a limited stack of chips playing against the casino, which has a nearly infinite supply. The gambler is bound to lose eventually. And these numbers show just how quickly the attacker loses. Let's assume an attacker has a massive 10% of the network's computing power. Even with that, after the honest chain gets just one block ahead, the attacker's chance of ever catching up drops to about 20%. By the time the honest chain is 10 blocks ahead, the probability of an attack succeeding is, well, it's basically zero. So here's the key takeaway on security. It's not that an attack is theoretically impossible. It's that it becomes computationally impractical so fast it might as well be. Once your transaction is buried under just a handful of blocks, it is, for all intents and purposes, locked in forever. And that's really the core of the 2008 white paper. Through this brilliant cycle of identifying a problem, proposing a solution, and then solving the new problem that solution creates, it builds a complete self-regulating system for electronic money. It leaves us with this huge question. What else becomes possible when we can exchange value based on pure mathematics instead of having to rely on trusting other people or institutions?